Hello, everyone. Welcome to my talk on real-time software and hardware video codecs. So the work I will be presenting today, it's work we have been done in our team, and I also took some results and illustration from other partners' work, and also give a reference for these works. So to start, we start with the context. The context of video coding is always the same. So we noticed this last year, a significant increase in the video traffic. And this increase is caused mainly by three reasons. So the increase in video streaming caused by the new video platform, like streaming platforms like Netflix, YouTube, and gaming platforms like Twitch. The second is caused by the new video formats in high resolution, 4K, 8K, high dynamic range, and 360 that also increase the bandwidth. And more recently, the COVID-19 has increased the part of traffic. And as we can see in this figure on the right, the video traffic have increased significantly during the last 5 years, and it's reached today 82% of the global internet traffic, which is very high. And also this contribute to around 1% of the greenhouse emissions, global greenhouse emissions. So this situation raises many challenges to the coding community. So the first one is to how to deal with all this content and increase in bandwidth to ensure a high video quality service with high video quality and very low latency. The second challenge is that today we have many video coding standards. Here I cite 5, like AVC, HEVC, EV1, EVC, and VVC. So this raises many challenges to how to select the right standard and how to ensure the interoperability between all these codecs. And as I said before, the third challenge is the energy footprint. Sorry, here it's footprint, which represents 1% of the global greenhouse emissions. And there is also an estimation that in 2025, the CO2 emissions of video streaming will reach the emissions of cars, which is very high, and we need to address this problem to decrease the footprint of video traffic. And the last challenge is today we have like many new video format at high resolution, like 8K, 360-degree bound cloud light field for more immersive video. And this needs to be coded efficiently to be transmitted and deployed in real environments, giving high quality of experience and immersive viewing of the scene. And they can also be used in many applications. So one mean to address these challenges is to develop a new coding video standard. And generally, we have one video codec each decade, as we can see here in this figure. In 2023, we have standardized, like jointly by ITU and ISO, AVC, Advanced Video Coding Standard, and in 2013, VVC has been standardized, targeting UHD and 4K resolutions. And in 2020, versatile video coding standard have been standardized, targeting also high resolution videos, 8K, 360, and high dynamic range. As we can see here also, for each standard, we have what we call the reference software that implements the reference decoder and also all the coding tools developed by the standard. For AVC, we have GM, for HEVC, we have HM, and for VC, we have VTM. So what we can say here briefly on VVC, we can say that VVC improved the coding efficiency compared to HEVC. This is what we will see also in the next slides. And the second The second improvement brought by VVC is the versatility. This is also very important tools. As we can see here, VVC in the first version supports many tools, especially, for example, for screen content coding tools, and also for resolution adaptation, scalability, and tile streaming. And all these tools are released in the first version of the VVC standard. This is giving us like versatility that we can use VVC in many different applications. So now this is the global context of VVC. Now, the idea of this presentation is not to present all the tools of VVC, but because I will spend more than an hour to present all the tools, there are too many. But I just want to give a brief introduction to what is new in VVC and focus on two tools that I will present in the next two slides. So first, here, these schemes give the global scheme of VVC encoder. What we can notice first that VVC follow the hybrid prediction and transform coding tools, architecture, which was used in AVC and HEVC also. So the first block here performs the block partitioning. Once we have the video partitioned into blocks, we will perform transform and quantization. This is transform and quantization. It is performed on the residual. The residual is the difference between the original and the predicted frame, which is encoded in intra or enter predicted. So here we have a third block, which is the decoder. So the encoder also performs the decoder, so it will perform inverse quantization and inverse transform to recover the residuals. And then with the prediction signal, it will use what we call in-loop filters that will enhance the visual quality of the decoded frame. That will be used then for enter, like temporal prediction. And here the frame before in-loop filters, it will be used for enter predictions. What is new in VVC? We have enhancement of the different tools at different level, like at the partitioning, at the transform, at intra and enter predictions. And also what is new in VVC is that we introduced one new in-loop filter, which is called adaptive loop filter, which wasn't exist in HEVC. And like we have many improvements at different level of the different tools, and all these improvements bring this coding efficiency compared to HEVC. Now I will try to present two tools, which are like the partitioning, we can see here, and also the transform that we apply on the residual signal. So the transform used in VVC, it is called multi-type tree partitioning. Like here in this figure, I give all the splits that can perform HEVC and VVC to partition a block. Usually a block, it is a CTU. The maximum size in VVC, it is 128 by 128 pixels. As we can see here in HEVC, we have only two splits. The first one is to do not split, and the second one is to split into quad 3. So VVC has introduced 4 new splits, which are like binary splits into horizontal and vertical directions, and also ternary splits that split the block into 3 parts, quarter and half size of the block, also in horizontal and vertical. And here we can see an example of splitting a block. So, and the tree on the right, on the left part. So first the block is split into quad tree, as we can see here in the first part of the split. And then each block is then split into quad tree or ternary tree or binary tree. And this will adapt the size of the block to the local activities of the pixels. And this block will then be encoded more efficiently with the different tools proposed in VVC, intra prediction, enter prediction, and transform tools. So this is the partitioning. As you can see here, the encoder will perform for each block all the splits at each level of the block. So as you can see, this will increase the encoding complexity because the encoder will process more blocks, and also enhance the coding efficiency because we will find the optimal partitioning with VVC better than with HEVC. So now, if we move to the next slide, I will present briefly the transform block used in VVC. So in HEVC, the transform block is composed only by this, what we call primary transform, and we use DCT2 mainly, or maybe DCST4 or DST7, but only for small blocks of size 4x4. In VVC, we have two improvements. So the first one is we use what we call multiple transform selection as primary transform. And in this multiple transform selection, we use 3 transform kernels, which are DCT2 of size up to 64, DST7, and DCT8 of size up to 32. And this provides some competition at the encoder side. So the encoder will make a decision to select the best transforms that compact the energy of the residual and separate also and decorrelate the signal between high frequency and low frequencies in the block. So this is what new in VVC is this concept of transform competition. So we can use many transform to select the one that minimize the rate distortion optimization. So this will increase the coding efficiency, of course, because we select the best transform, but at the same time, it's also increase the encoding complexity because we have to test all these transforms at different block sizes, which significantly increase the encoder complexity also. So the second new transform used in VVC is what we call it a secondary transform, and it is called low frequency non-separable transform. So usually non-separable transform are very old in signal processing and image processing, but they are not used in video standards and image standards for their high complexity compared to the separable transform. Like separable transform, we can do vertical then horizontal transform separately. In non-separable transform, we perform both in once, but it is actually more complex. And in VVC, we introduced this notion of secondary transform, and it is applied on the residual which are already transformed by the primary transform. As we can see here, we first perform MTS, multiple transform selection, first primary transform, and then we may also perform this secondary transform, which is called which is non-separable transform or LFNST. And at the decoder side, we will perform inverse LFNST and then inverse MTS. So this is the transform module in VVC. So here in the figure on the right, when we receive, for example, the signal at the decoder side, first, if the LFNST was enabled at the encoder, we will perform the inverse LFNST. Here we have 8 kernels, different kernels for the LFNST. And then we will perform the MTS, vertical and horizontal transform. And here we have many configuration, whether we use DCT2, DST7, or DCT8 for the horizontal and vertical direction of the block. So briefly, I introduced like what it is VVC, a new standardized in 2020, July 2020. Then I said that it's the main concept of the hybrid video codec with the transform and prediction. And also I presented in more details 2 tools, which are partitioning and also the transform modules. And for more details about VVC, there is this review paper I cited in the second slide. You can go through and see other tools. So today I want to focus on more the performance on VVC in terms of coding efficiency and also in terms of complexity. In this figure, I give the bitrate reduction in terms of PSNR of VVC with the VTM implementation compared to HEVC with the HM implementation. And here, what is the bitrate reduction? Actually, it is what VVC can offer in terms of bitrate reduction compared to HEVC for the same PSNR quality. And here, I give this performance for different configuration. Here, AI is all intra, RI is random access, low delay B, and low delay P. So actually, AI is intra, and other configuration are enter coding configuration. And here in this figure, I give here the BD rate gain, so the rate rejection for the same PSNR of different version of the VTM developed during the standardization time between 2018 and 2020 with respect to HEVC. As we can see, the rate has the gain in terms of rate, like negative is better, has been increased between the second version of the VTM to the 12th version of the VTM, which was released recently. What we can see also, like for all Anshra configuration, we have 25% of bitrate reduction, and for random access configuration, which is used in broadcast and streaming, it's offer around 38% of bitrate reduction compared to HEVC. And compared to the second version of the VTM, we mainly moved from 23 to 38 for random access, and from 17% to 25% for all Anshra, which is significantly important in terms of gain in video coding. So to summarize this slide, in all Anshra, we have 25 bitrate gain compared to HEVC, and in random access, we have 58% of bitrate rate in terms of PSNR. Now, in terms of, we all know that PSNR is not a good metric for quality evaluation. So we performed here at INSA and become some subjective evaluation of VVC compared to HEVC. And we selected some videos. Here I give some performance of visual quality compared to bitrate for this cat and a robot 4K video sequence. It is 4K video, but here I give two curves, one for HD resolution and one for 4K resolution. In this figure, we show the MOS. The MOS is the mean opinion score of the viewers that view the videos with respect to the bitrate. And the dot curves here represent VTM, and the lines here represent HEVC. As we can see here, higher MOS is higher quality, and the MOS value between 80 and 100 correspond to the excellent quality area. We can see with VVC, we can have 50% gain. We can halve the bitrate from 6 to 3 for HD resolution to reach this excellent area of quality. And for UHD, we can also halve the bitrate almost from 14 to 7 megabit per second to reach this very excellent quality area. And as we can see here, the black dot, it corresponds to the reference video, which is the video, the original video not encoded, which is always in this excellent quality of area. So what we can notice here with very low bitrate, 3 megabits per second and 7 megabits per second, we can reach this reference video at low bitrate. And actually VVC can halve the bitrate for this particular video sequence. Now, I give some performance of our study because we performed this study on not only one video, but on 7 video sequences. We can show here the characteristic of the video in terms of spatial and temporal information. So we have diverse video. We downsample this video into HD resolution because the original resolution was 4K, and then we encoded them in both VTM and HM at the same quality. And here I give some bitrate gains for HD resolution and UHD resolution. For different metrics here, we use PSNR, SSEM, VMAF, and the MOS. As we can see here, we can increase the bitrate reduction from 31 to 37 when we rely on more subjective evaluation experiments for HD, and for UHD from 34 to 40% of bitrate reduction in terms of MOS. What we can see here, in average, like VVC can offer up to 40% of bitrate reduction for the same visual quality for the 7 video in HD and UHD resolution. Now, if we move to the complexity of VVC, so things are a little bit different in terms of complexity. In these curves, I give the complexity of the VTM, different version of the VTM from VTM2 to VTM12 with respect to HEVC, HM. 100% is the same complexity, and for example, 500% is 5 times more complex than HM. As we can see here, all Antra configuration is more complex than other Enter configuration. And the complexity has been also increased a little bit from the first version to the last version to end up with 25 with an encoder which is 25 times more complex than HEVC in all Antra configuration, which is quite high. For Enter configuration, we started around 4 times more complex than HM, than HEVC, and we end up for random access configuration by an encoder which is 8 times more complex than the HM. So what we can say here is at the same timeline with enhancing the coding efficiency, according to the figure I showed previously, we also increase the complexity of the encoder for both random access and Antra configuration. But the complexity is very high for all Antra configuration. Now, this is about the encoding parts. Now, about the decoding parts, we can see here the same measurements. Here we have the complexity of the VTM, different version of the VTM decoders compared to the HM decoder. What we can notice here is the complexity of the decoder is very low compared to the increase of the complexity of the VTM encoder. Here, the complexity of the decoder, whatever the configuration we have and the different VTM, the complexity remains lower than 2 times the complexity of the HEVC decoder. This is very good for the standard because the complexity of the decoder is very important because we will deploy the VVC decoder in many mobile platform devices. So we have to keep the decoder complexity very low. And this was very successful for VVC because the decoding is very low. Doesn't exceed 2 times the decoding complexity of HEVC, which was not too high also compared to AVC. Now, I want to show also the complexity repartition of the coding tools in the VTM decoder. What we can see here in these 2 figures, we have the different coding tools like entropy, motion compensation, inverse transform, deblocking, SAO, like in-loop filters. On the left part, it is for HEVC, and on the right part, it is for VTM. There is one main difference between the complexity repartition of these 2 decoders, which is caused by the ILF. As I said before, adaptive loop filter is one new filter added in VVC, and it is the most complex part of the decoder. And it represents, for example, here, 37% of the decoding time of the video in UHD resolution in random access configuration. And this actually changed the repartition of the coding tools in VVC compared to HEVC, because in HEVC, we don't have this ILF filter. So this ILF filter is one of the most efficient tools in VVC. It's bring, I think, around 4% of coding gain, but it's increased a lot the complexity, especially of the decoder, and also change the repartition of the complexity of the decoding tools between HEVC and HEVC, between HEVC and VVC. So what we can see here in this figure, like the complexity repartition of the tools in VVC and HEVC is quite similar. The main difference came from the ILF in-loop filters, which is new in VVC and which is very complex at the decoding at the decoder time. So now we have seen like some performance of VVC compared to HEVC in terms of coding efficiency and also in terms of complexity. Now, as I said before, we have now in the literature many video codecs, and it is important to see what is the position of VVC with respect to this other codecs. And in these 3 slides, I will give some information about the comparison of VVC compared to 3 other standards, which are HEVC with the reference implementation HM, and also essential video coding, which is also developed recently in the same time then with an VVC by MPEG with its reference software, which is called ETM, and also the codec developed by AOM, which is AV1, and through its implementation libaom. And this study has been done by our colleagues in Interdigital. I give here the reference. They compare these 4 codecs under the VVC common test conditions. So we use the same sequences of the VVC test conditions, and also all this video are encoded in random access configuration with 1 ANCHA frame per second. And to compare this different codec, we use also the BD rate, which gives us the rate gain with respect to the reference. And here the reference is HEVC. So we always compare VVC, EVC, and AV1 with respect to HEVC. And we give here in this table some numbers of rate reduction in terms of PSNR, in terms of multi-scale SSEM, and also in terms of VMAF. What we can see here that of VVC enables the highest gain compared to HEVC with respect to AV1 and AVC. So we can reach BD rate reduction with respect to HEVC around 36% in terms of PSNR, and also 36 or 37% in terms of VMAF. And this is reduced to 14 only for AV1 in terms of PSNR and 18 in terms of VMAF, and around 21 to 27 for EVC. What we can see here for the different quality metrics, whether it is PSNR, MSSSEM, or VMAF, VVC is always performing the highest bit rate reduction compared to the HM when we compare it to AV1 and also EVC. Now, if you want to compare these 3 codecs, we have also to take into consideration the complexity. This is very important. And these 3 codecs like VTM, libaom, and ETM have been also compared to HEVC in terms of complexity of both the encoder and the decoder. What we can see here that VVC is 13 times more complex than HEVC. AV1 is around 5 times complex than HEVC, and EVC is 7 to 6 times more complex than HEVC. The decoder complexity is a little bit different because all these codecs and standards keep the decoder complexity very low. Maybe VVC is the highest, is the most complex with 2 times more complex than HEVC, and AV1 has decoder which is even lower, less complex than HEVC, and EVC is more close to the complexity of the VTM. So if you want to compare these three codecs, I drawed here in 2D plan the BD rate gain. Here it's the value, it's a gain, so the values here are negative. In terms of the encoder complexity versus the encoder complexity, and here is also the gain, also in terms of VMAP with respect to the decoder complexity. And here, like yellow is the HM, so all the, as I said before, all the codec are compared to the HM. So the HM is in the bound 0, 100, 0 for BD rate and 100 for the complexity. The second codec in orange is AV1, which is less efficient than the two others, but also less complex. And then came the ETM, the VVC standard, which is more efficient than AV1, but a little bit more complex. And then in blue here, we have VVC, which is more complex in terms of encoding, but enable also the highest coding efficiency. What we can also notice that to go from 30 to 40% of bitrate gain, the complexity is significantly increased, is almost doubled from 7 times to 13 times with VVC. So like what we can see here, like to reach this 40% to go from 30% to 40% of bitrate gain, the cost in terms of complexity is very high, and it is almost doubled with VVC. So in terms of decoder, things are a little bit different because all the codec are not very complex in terms of decoding complexity. So all the complexity are lower than 2 times, even if VVC is represent the highest complexity than the essential video coding. And as we said before, like the AV1 decoder is less complex than HEVC decoder and still provide a good gain. And then this is HM, and this is AV1, which is less complex and perform 20% gain compared to the HM. So this is very nice study that give us the position of VVC compared to other competitors like AV1, HEVC, and also EVC standards. And if you want to go further about the complexity and the coding efficiency of the VVC tools, I give here also a second reference of Interdigital, that where they did a good evaluation of the complexity and the coding gain in VVC by tools. So for the last part of this presentation, I wanted to talk a little bit about OpenVVC Decoder. So as you may know, OpenVVC has been developed by INSA IETR lab. So what I can say today about this decoder is like today, OpenVVC is publicly available under LGPL 2.1 license, like available in open source. And so far we have performed 3 releases. So one release in the end of March, one release in April, and we are expecting the third release the next Friday, like this week. And here I give also the link to the GitHub link of the OpenVVC decoder. What we can see, like OpenVVC, it's a library that's enable real-time decoding of VVC bitstream. It is real-time and it is also cross-platform. It can compile it on Mac OS, on Linux, and also on ARM, Windows, etc. So what is OpenVVC supporting today? So in the next release, we are expecting to have all Antra tools, like all transform and in-loop filters. And with these tools, we will be able to support the decoding of all Antra, like the common test condition in all Antra configuration. We also have support of two kinds of parallelism. The first one is the tile. So first, each frame is partitioned into tiles, and the tiles represent the different region of the image that can be decoded in parallel uh, by the OpenVVC decoder to leverage the multi-core platforms. And we can perform also the frame parallelism, that different frame can be decoded in parallel. We also support a sample version of enter configuration. We are supporting enter configuration, but we don't have yet all the random access configuration tools. We will add these tools progressively during this month, during May. And we have some SEMD optimization. So it is low-level optimization for Antra tools and Enter tools for Intel x86 platform that enable also to increase the decoder speed. And we also, finally, we offer a support with two players, which are FF Play player and GPAC player. Just to remember that with OpenVVC Decoder, we have realized the first word demo of streaming VVC content. It was done with our partners ATEM, SES for the satellite, and also VLC for the player. So first, the Explorer bitstream are encoded with the ATEM encoder, packages transmitted via DVB S2 over the satellite, and then received by the DVB-S2 receiver, and then decoded with the OpenVVC decoder in real time. It was the first word demo showing like the end-to-end streaming of video with VVC. I give here some performance of the decoder on a laptop with Intel processor. We can perform a very high frame rate of 130 frames per second for 10 megabits per second VVC bitstream in 4K resolution, and around 95 frames per second for higher bitrate, which is here 20 megabits per second. And here just illustration of our demo with this demo with a VLC player decoding VVC content with using OpenVVC decoder. So this is for my presentation. So to conclude, I would like to give some conclusion and future works. As we have seen today, the complexity of VVC is at encoder size may be a real issue that we have to address. So we have some work and many work need to be conducted to try to reduce the complexity of the VVC encoder. And here we can use also AI to help or guide the decoder to take the right choices without testing the different configuration, which is very complex to perform in real time. The second challenge also is to continue the development of the software VVC encoder and VVC decoder. So HHI are providing open source video VVC encoders, which is called VVEnc. And we are also working on the decoder with the OpenVVC project. And we are expecting many improvements in the few coming weeks. The third challenge is also to be able to provide hardware VVC encoder and decoder. We have also some collaboration on these works to build hardware blocks, for example, for the transform or also for the ALF, that can be then included in hardware VVC encoder decoder, or just to accelerate or speed up the software decoder or encoders with hardware devices. One third point, which is also very important, is the energy modeling of the VVC codec, encoder and decoder, and also try to optimize the energy consumption of this codecs. This is also a challenging topic of research that are investigated currently and will be also addressed in the future. For this topic, we have two events we are organizing in the future. So the first one is special session at the PCS workshop, which will be held in Bristol between 29 June and the 2nd July. We have a special session on AI for VVC optimization and enhancement. And there is also a special issue we are organizing at the IEEE Transaction Journal on Consumer and Electronics that also target real-time implementation of VVC standard for consumer electronic devices. And in this presentation, I give the different links to access to this events. And also I give a reference to the VV encoder developed by HHI. So the next part of this conclusion is if we have to go further in terms of research in this area of research, there is a lot of research about enhancing the quality and providing scalability with using AI like artificial intelligence or deep neural networks. And also the last points, like the next generation of the codec maybe would be rely on autoencoders or what we call learning-based video coding or image coding. And we have also some work on this area of research. And we are organizing two events. The first one is the GDR workshop, expected in 15th June, about learning-based coding for digital image and video information. We will have, I think, a nice program with some guest speaker experts in this field of research. And in this research also, I will give my next talk on 24th June about also this learning-based image and video compression, like giving presentation about the recent solution and the progress and the challenges of this field. So thank you very much for your listening, and feel free if you have any question, I will be happy to answer.
Thank you very much. So I can start the questions. I have some. So first of all, thank you for this talk. It was very interesting, as always. Okay, I have a first, maybe a silly question, a simple one. Can you go back to slide 8, please? It's probably, yeah. My question is the obvious one. What happened between VTM 11 and 12? Why is the efficiency decreased so suddenly between the two versions?
Yeah, I think, yeah, this is, I think, good to notice this because when I was reporting these results, like we have seen here that the efficiency was increased above 40% of bitrate reduction, then it's go back to 38, which is not nice. And I think it was, there is a bug into the reference software that leads to this this improvements in performance. It was good news, but for just a few times, just for 1 month. And then we come back to the reality with the VTM 12 with the correction of this bug. Yeah. Because it's surprising to see this huge increase of 3 to 4% in after the VTM 10, which should be like referred to the standard.
Okay, so we have 3 raised hands. So okay, the top one is Luce in the order of the participants. So Luce.
Okay. Well, I put my camera maybe. Okay. Well, thank you, Wassim. I have several questions, but maybe I can just ask a few ones. On OpenVVC, does VVC Enc use OpenVVC? I mean, in the encoder, you need a decoder. Is it OpenVVC or is it another one?
Yeah, actually, VV Enc also have a decoder. So they developed a decoder. So today we have two two software real-time decoders, VVDec and OpenVVC. The main difference between both is like OpenVVC is developed from scratch in C++, and VVONC irritate a lot from the reference software VTM. It is developed in C++. So I think in the future, we will have many advantages in terms of portability to mobile devices, very low memory consumption, but actually we need to integrate more tools, because when you irritate the architecture from the VTM, you support by default mainly all the tools. So for us, we have to integrate new tools because the decoder is developed from scratch, but we will have more advantages from the C implementation, the optimization, the friendly parallelism, and also the integration into mobile devices with very low energy and computing resources.
Okay. And if you would put OpenVVC in your graphs of comparison, you have an idea where it would be of performance versus complexity?
Yeah, I think today I didn't yet, I don't want to, I didn't give performance about OpenVVC because we don't support yet all the tools. But I think in the implementation we have tested with our partners on the configuration we are supporting, we are faster. And also we have, I think, 5 times less memory than the SSI decoder, but of course we are not yet supporting all the tools, so we are waiting for the next months to actually do a good comparison and write paper about that, and we will have other talks about these topics.
Okay, maybe just a question about the partitioning in VVC. Once you have a partition in binary or ternary, can you still use all the modes to to go on the partitioning? I mean, a binary partition, can you do a 2x2 partition on the one of the sides? I don't know if this is clear question.
I don't understand the last question.
On your example here, you have a binary, ternary division, and then it is still divided in 2. But you could not divide a rectangle in 4. Can you divide a rectangle in 4 parts, for instance?
Yeah, there are some restrictions. For example, when we perform ternary or binary, we cannot do, for example, quaternary. There are some restrictions because they lead to the same partitioning, for example, or we are not anymore square, so it's difficult to have quaternary. There are 2 kinds of limitation. So there are some limitation by the standard. So for example, we cannot use quaternary after binary tree or ternary tree. And there are some limitation to gain in terms of complexity, because it is not efficient in terms of coding, but if we test it, it will take a long time to test.
Okay.
It is allowed by the standard, but we know that it is not efficient, so we disable it in the reference software.
Okay, thank you, Wassim.
Okay, next maybe we have the guest from Interdigital. So Philippe, I think you can ask your question.
Thank you. So for the clarification, whether there is a drop of performance for VTM 11, it's for, can we see? Okay, so maybe, I don't know if it is the case, but probably it is the case. Wassim, in the VTM 11, they have introduced in the encoder MCTF preprocessing, where they pre-filter the image to reduce the noise, and they have a big gain, but it's encoder trick.
Yeah, it is not standard.
Yeah, so I think that's the reason of this drop. So yeah. My question was about the speed up work you did in your code. I think you didn't implement the wavefront.
Yeah, not yet. We don't have wavefront parallelism. We have only tiles and frame level parallelism.
And you will implement it later, maybe?
Yes, actually, we drive also our implementation by the requests we can have from our partners. So, for example, if the encoders say like, yeah, we are using wavefront, of course, we will integrate wavefronts. As we can see today, they use the tiles. So we implemented the tiles parallelism, which was priority. The frame parallelism, it's independent from the encoder decision. So we implement it because we can enable it, whatever the encoding choices. But yeah, the next step is to add it like this wavefront parallelism. But it was not priority because it's not yet used by our partners.
But maybe you can add the two parallelism with tile plus wavefront, and potentially you could have even more speed up.
Yeah, we can now. I think it is allowed in VVC to use wavefront parallelism inside the tiles. And what we are doing today, we have the right infrastructure to do it, because today we can also use frame parallelism and also added tiles parallelism. So we can do the same for tile parallelism and go further with deeper with wavefront parallelism.
Okay, thank you, Wassim.
Welcome.
I think Michael is next.
Yes, question regarding the overall complexity of the system. Is it bounded by memory? Is it the limit is more memory bound, or is it more compute bound in general? Or maybe there are probably different parts in the encoder which may have different limits.
Yeah, I think the main issue today is about computing complexity, which is significantly increased. And there is also memory increase complexity, but it is mainly related to the implementation. For example, from one implementation to the other, we can reduce a lot the memory. And this is, for us, with OpenVVC, it is important because we developed the decoder working very locally, only on the block and the surrounding block. And this is decreased a lot the memory compared to other implementation. And we think this is important, for example, for when we go, for example, for mobile devices where the memory is limited.
Okay.
But the main challenge is first maybe computing, and then memory.
So we have no raised hands, but I have additional questions. I have another question about the energy consumption. Is there a global study of how much energy is consumed by the different parts of the processing? And by that I mean you consume energy when you encode the video, when you transmit it, and when you store it, and when you decode it. And probably depending on the type of video, you will consume it differently, and it may have a different impact. But my question is there a kind of study that says, okay, for example, if you have a video that is going to be viewed many times, then maybe it is worth spending much more complexity and much more computation energy when encoding it, but you should limit as much as possible the bandwidth and the computation when decoding it? And is this something that has been measured in order to know how you should minimize the computation, the energy of the different parts of the computation and storage and transmission of the videos?
Yeah, I think it is a very good question because this is the next area of research. We are I think in the 2 or 3 upcoming years, there will be many research about these questions you are asked. We are working on that, of course, to try to model the energy of the decoder, of the encoder, of the streaming, of the transcoding, and also how to use this energy to select the best coding that minimize also the energy. We are developing, we have many work in progress, but we don't yet publish on that. But in terms of some results, there is recently a model proposed by Netflix and Bristol University, but it is more commercial to predict like the CO2 consumption of streaming. But yeah, there are many works in progress. I think we will see a lot of results about that, both for models and also for the estimation, and also to take the decision to minimize the energy. I think many research will be dedicated to that in the upcoming years, and we are targeting this area of research, which is very important, I think, also. But yeah, there are some research, but we can wait a little bit to have all the answers.
Okay, thank you. Do we have another question?
Yeah, for the energy, it is very hot topic of research. So
yes, which is a good thing. Okay, well, it seems like we don't have any other questions. So thank you again for your talk.
thank you for your listening, and yeah, have a nice evening, and see you soon.